Welcome to another video on SRD Cloud. So in this video I want to talk about container storage interface, which is a storage architecture for Kubernetes or any of its implementations like OpenShift. So in this video I will talk about how to develop a container storage interface and how to build it and how to publish it in an image registry and also how to use it and what are the use cases involved, the entire story behind the storage architecture in Kubernetes or OpenShift environment. So let's get started. So what is container storage interface, shortly called CSI? Let us build a story behind this. Docker is the container environment tool. Using Docker you can create containers, and the containers can house your workloads or applications. And Kubernetes is the orchestrator of such a container environment, because otherwise it will be very difficult for you to manage hundreds and hundreds of pods and hundreds and hundreds of containers, and how to manage them, how to scale them, how to deploy them, and so on. So Kubernetes got a good job in orchestrating all this. And in the container world, from Kubernetes perspective, pods are the basic blocks. If you want to deploy your application, you will end up deploying a pod using various methods. And these pods contain one or more containers, and each container is represented by an image from an image registry, and these images are what carry your application workload, the code that you write along with the basic, very trimmed operating system. And these pods are deployed not only on one worker node, but it can be deployed on many worker nodes based on your need. And the container inside the pod executes the business logic. And obviously any application in computer science, along with networking and computing, will require storage as well. And there are two types of storages in this environment. One is the ephemeral, which is the storage is temporary and it is there for the application to run, and when the application terminates, the storage goes away. The other type is a persistent storage, which is a standard, not a temporary but permanent storage for the application. That means the application can attach itself to a persistent storage, and it can read or write data from or to it, and then when the application goes away, the storage stays on, and the same application can come back again and access the same persistent storage again. So this is very much a requirement for container applications these days. When the containers started, they were very happy with ephemeral storage. They started running, and then they executed something and created some data and got copied over to somewhere else, and then the application got terminated. So the need for storing the data permanently was not there. But later on, when the containers became mainstream in what is happening in today's computing world, persistent storage has become very, very important and critical part of container computing. And in this video, we are going to talk about one architecture to provide persistent storage for containers and the applications and workloads and pods in a Kubernetes or OpenShift environment. So let's move on to the more details. Here are the use cases for the container storage interface. So first of all, whatever program that you write, whatever architecture you design and develop, it has to be registered in the Kubernetes or OpenShift environment. And then when you create what is called a persistent volume claim or persistent volume, the corresponding volume has to be created somewhere according to your environment. So in one such example where the storage is offered by a SAN storage, for example, the SAN storage is connected to the SAN switch, and then SAN switch is connected to the worker node. So in that case, the CSI implementation has to go out to the storage provider and create the volume whenever a persistent volume claim is created. And we're going to see how that is done. And then when the persistent volume claim is created, it has to be attached to a pod. Otherwise, there's no use in the persistent volume claim. So when such a thing happens, when a pod is created with the persistent volume claim in it, then the volume needs to be attached to the corresponding worker node. And finally, it has to be attached to the pod as well. So when the pod comes up and then running, then the application workload inside the pod in the form of a container can read or write data into the persistent storage, the volume that we're talking about. So I'm going to go into the details of all this. For now, just focus on the use cases involved in CSI. So here is the CSI reference model. So this is how the CSI fits into the Kubernetes or OpenShift environment. So there is a master node and there is a bunch of worker nodes, and there could be a bunch of master nodes as well. Then we will end up developing what is called a stateful set with 3 containers in it. The CSI provisioner sidecar. Don't worry about the term sidecar. We're going to go through all this later in a few minutes. And then there's something called liveness probe for health monitoring purposes, and then the CSI plugin that we're going to develop. So there will be 3 such stateful sets, one for provisioning, which will be responsible for creating and deleting a volume, and a CSI attacher sidecar whose responsibility is to attach the volume to the worker node and also attach it to the pod and all that. And CSI resizer sidecar, its responsibility is to resize already created persistent volume claim or persistent volume. And then we will end up developing what is called a daemon set, and this will contain the CSI plugin which will perform the necessary operations of mounting the volume to a particular pod that is corresponding pod which is getting created. And then the node driver registrar sidecar, and that is responsible for registering the CSI plugin in the CSI environment, in the Kubernetes or OpenShift environment. So in this diagram, I also have external storage provider. So the storage can be external, it can be internal as well to the worker node. But anyway, the storage needs to be represented somewhere in this environment, so I did that. The CSI plugin will be talking to the external storage provider or whatever API there is out there to create the necessary objects on the storage provider or on the worker node. So this is how the entire CSI architecture fits in. So now let us see how such a CSI plugin can be built, and it can be deployed as well. So I will end up developing a Go language based application, and it will have a startup, and I'm going to do something very specific in the startup code. And then I will end up creating what is called a gRPC server. gRPC is the Go language specific RPC server for distributed computing, and it will listen to a Unix socket which is determined by or defined by the CSI specifications. And then I will end up developing 3 distinct modules. One is called the controller, and one is called the node, the other one is the identity. We are going to go through the details in a moment. And after building the Go language application, I will enclose it with a Docker file and create an image. And I will push that image to my favorite registry, either Docker Hub or Quay.io or Artifactory, whichever is applicable in my case. So this is the methodology we are going to use to produce the CSI plugin. Now, what exactly is the controller? The controller's responsibility is to create and delete, and also to attach and detach the volume to the worker node. So create and delete a volume, as well as attach and detach the volume to the worker node. So as we saw earlier in the use cases chart, when a persistent volume claim is created, then the CSI provisioner sidecar will get notified, and that sidecar in turn will figure out what is the corresponding CSI driver. And to do that, the persistent volume claim will have a reference to the storage class, and storage class will have a reference to the CSI plugin driver. So that is the connection between persistent volume claim and the CSI plugin. So through this route, the CSI plugin's controller create and delete all those methods will get invoked when the persistent volume claim is created or deleted. Similarly, when you attach the persistent volume claim to your pod, then through the same path, the controller will get invoked to attach the volume to a specific worker node. So that is the responsibility of the controller. And these are the methods that I will end up implementing. We are going to go through the details in a few minutes. I'm going to show you the actual code that implements all this. So similarly, node. So once the volume is created and also attached to a worker node, it has to be mounted on the worker node to the pods. So it is generally done in 2 stages, and I will explain why 2 stages. The first step is to mount the volume to a directory that is global to all pods inside the worker node. And then the second step is to do a bind mount of the same thing, the mounted volume, to a pod directory. So why is it done in 2 stages? This will facilitate sharing of the persistent volume claim across pods. So if otherwise, then when a pod is created with a specific persistent volume claim, then the volume will be mounted on the worker node, and then it will be attached to the pod directory. And if another pod uses the same persistent volume claim, then the code will try to attempt to mount the already mounted volume directory on the worker node, so which will fail anyway. So this will facilitate sharing of the volume across pods, but within the worker node. And finally, so these are the methods that I will show how to do all this. And finally, the identity CSI specification also includes this identity module to monitor the health of the CSI driver. If for some reason the CSI driver inside the worker node crashes, then the community environment or OpenShift environment will not even try to create the volume or attach and detach or delete the volume, all those necessary steps. So this module will monitor the CSI driver by simply invoking a particular method in the CSI driver, and unless there is a return value, then the driver will be considered offline. So these are the methods used for health monitoring purposes, and I will show you how to implement these as well. So now once the CSI plugin application is developed, as I said earlier, I will enclose it with a Docker file, and then I will push it to the my favorite registry like Docker Hub or Artifactory or Quay.io and things like that. So once it is done, my application is up and running, up and available on my favorite registry. Then how do I consume it? I already talked about stateful sets and daemon sets and so on. So that is what needs to be done next. So the stateful sets and daemon sets can be deployed in a Kubernetes or OpenShift environment in 2 different ways. One is using the template approach, where you create a template with parameters, and then define all these specifications, stateful set specification and daemon set specification and so on. And then during runtime, the parameters and their values will be filled in the characteristics of these things. The other option is to develop an operator, and I will do a separate video on that one. That is the formal way of developing anything in Kubernetes these days. You need to create a custom resource definition and then a corresponding operator, and then implement or deploy these two things inside the environment. And then whenever you want, you create a custom resource, and that will cause the operator to wake up and then create all these stateful sets and daemon sets and all those things inside the environment. So there is another approach, but in this video we will talk about the template approach. So in the other section down below, there are some artifacts like config map and storage class and security context constraints. We will see all these things in a moment when we actually see the code. So now it's time for us to take a look at the actual code and also a demonstration of the CSI in the real live OpenShift environment. So let's switch over to that. So here is my GitHub repository where I implemented a CSI spec, and I intentionally left certain things blank so you can fill them up. You can clone or fork this source code and develop a CSI driver in absolutely no time. If you have all the APIs to create and delete a volume or attach and detach your volume to worker node and pod and all that, you can develop such a CSI driver in no time. So let's start with the make file. So let us start there. We just got only one line in it, that is src build.make inclusion. So let's go there. So src build.make. So here I defined my driver name, my CSI driver, and I'm going to push it to my repository, my image registry repository is svenkat.doc on Docker Hub, and the 1.0.0 will be the version of this driver. And this section is where the Go language code is getting compiled, and the output of the executable is copied to _output directory, and then I also copy it back to src directory for some reason, which I will explain in a moment. And I have a separate paragraph for Docker login so that I can push the image ultimately into my Docker Hub registry. And this step is to build the image after building the executable, and this step is to save the image to a tar file, and finally push the image to the image repository, the registry. So now let's take a look at the glide.yaml. So glide is a Go language package management tool, and in this glide.yaml I simply specify all the dependencies, and these are the dependent packages that are needed for the Go language to build. So this file will be used while building the executable later on. So now let's go back, and now let us take a look at the startup code, which is under cmd main.go. So there are a bunch of imports there, nothing fancy, and here is the reference to the driver I'm building. And these are the variables which I will be passing from outside. When we look at the deployment template, we will understand what exactly are these variables. So these variable command line parameters are parsed, and then the handle method is invoked, which is defined right here. And here I create the CSI driver object, and then I initialize it, and then I run it. And for initialization, I get the driver name and then the vendor version, node ID, and all that. This node ID is the name of the worker node on which this driver will be running. Remember, we talked about daemon set, where the worker node will be housing the daemon set. So now let us take a look at these three methods: the get CSI driver, initialize driver, and run methods of the driver. And they are defined under CSI Plugin, mycsi.go. So this is the driver I'm talking about, and it has the name, vendor version, and the node ID in it, and it has references to the controller node and identity server we talked about earlier. And each of these server components have capabilities built in, which we will take a look in a minute. And these are the arrays to maintain those capabilities. And get CSI driver, here it is, and this creates the new mycsi driver object. And then here is the initialize driver method, which does some validation. The driver name cannot be empty. And then the plugin initialize method is invoked, which is defined here, which does nothing actually. For future reference, for future purposes, we can add some initialization there in case if CSI specifications change. And the local variables are all filled. And for the controller capability, I set the access mode. So what this means is this driver will support deploying the volume claim across all nodes, and also provide read and write capabilities. That means this is a full-fledged driver. Nothing is hidden from this driver at all. And then this means the driver will support create and delete volumes, obviously, that is needed, and publish and unpublish volumes. That means obviously the driver will support attaching the volume to the worker node and detaching it from the worker node. It also supports expansion of the volume once it is created. And these two mean obviously the mounting of the volume to a pod, or to a directory, global directory on the worker node, as well as to the pod directory on the worker node. That is what the stage and unstage and expand volume mean. And finally, the identity server and node server and controller servers are all initialized with the driver object. And these three are also defined here. This is a very straightforward object initialization. And finally, the run method is what gets invoked. And the run method should be here. So in the run method, the most important thing happened, that is the gRPC server is getting created and it is started, and then the code goes into the wait mode, so that this executable running on the worker node in the form of a container in the daemon set will listen to any incoming request forever until the pod is killed. So now let's take a look at this gRPC server, where it is defined, and also the start methods. So let me go back to server.go. That is where these methods are defined. So here is my non-blocking gRPC server object definition. It contains start and wait and stop and force stop methods defined. And this is the start method, where the serve method of the gRPC server is invoked. And the serve method is the one that serving the gRPC server, custom gRPC server. It looks at the endpoint. It is in the form of a Unix socket. We will talk about that in a moment. and this code will validate whether that Unix socket definition is validated properly or not. And then the listen object is created on the Unix socket object, and then the server starts. Before the server starts here, the controller and identity and node components are registered into the CSI environment, so that when a persistent volume claim is created with the corresponding storage class, which contains the corresponding CSI driver, which is this one, then the CSI core in the Kubernetes environment knows, along with the sidecars, which code to invoke, which driver to invoke. Similarly, when the pod is created with a particular PVC claim, then for attaching and detaching purposes, which code to invoke. So those things will be determined because of this registration. So now it's time to look at the actual code. What we looked so far is only the startup code. So now let's take a look at the controller server, and this implements, let me look at the create volume and delete volume first. So here is the create volume method. So you will, so first of all, a validation is performed to make sure the create volume is enabled on this driver. Obviously it is enabled, but this check is performed to ensure that. And then the rec.getName will give you the name of the requested volume that needs to be created, and the size also. So along with the name and size and other capabilities, in your code you can go and create a volume. So I just commented out a lot of things here. You can use these to verify whether the requested volume should support multiple node and multiple read and write capabilities or not. And once you create a volume by invoking your own API in your environment, but whatever is applicable in your case, make sure you collect a unique ID of that volume and then return it back along with the create volume response object. So once again, this method will be invoked when the persistent volume claim is created, and that persistent volume claim should have a storage class associated with it, and that storage class should have a volume driver associated with it, and this should be the volume driver for it. If this is the volume driver for it, then this method will get invoked. And delete volume does exactly the opposite. You are given the volume ID that needs to be deleted. So this happens when you delete the persistent volume. This will not get invoked when you delete the persistent volume claim, because when a persistent volume claim is created, persistent volume is also created if required, and to get rid of that volume you need to delete the persistent volume object, not the claim. So now you created the persistent volume claim, and that in turn results in persistent volume if it is not there. A matching persistent volume, if it is there, then that will be used and bound to the persistent volume claim. And then when you create a pod with the persistent volume claim reference in it, then the volume needs to be attached to the worker node if this is done for the first time on that worker node. So that is accomplished by invoking the publish method, the controller publish volume method. So in this method you get the node ID, which is the worker node name, and the volume ID. So with the help of these node ID and volume ID, you invoke your own API or some legacy application program or whatever that is needed to attach these two. Generally, when this happens, as soon as this is completed, the volume will surface on the file system under dev directory if it is Linux. Obviously it will be Linux. That will ensure that the volume attachment went through successfully. So you need to verify that also here. So after invoking your API to attach the volume to the node ID, which is the worker node, you have to make sure that volume attachment went through fine. You should look for maybe a file or whatever that is applicable in your environment. make sure the attachment went through successfully, and only then you return from here. So this will ensure that by the time this method is invoked, the volume is attached to the worker node. So don't worry about the pod yet. This is only at the worker node level. And unpublished is the opposite. When you delete a pod, for example, and if that pod is the last pod carrying that specific persistent volume claim, then the volume needs to be detached from the worker node entirely. So that will happen through this method. So once again, you are presented with the node ID, the worker node name, and the volume ID that is involved, and you perform the detachment. And you not only perform detachment, but also make sure the volume surfaced on that file system on the worker node also goes away. So verify all that, and then you quit from this method. So this controller also supports snapshots, which I have not implemented in this case, but you can do the same thing. Whatever you see in the other methods, you can create a snapshot and you can delete a snapshot. You'll be presented with a volume ID, and you can return the snapshot ID and all that, and then you can delete the snapshot. You can list all the snapshots that are available for the CSI driver. So that's all about this particular Go program. So now let us go to the node server, and there are 4 important methods in this Go code. So let us go to the first set, which is stage volume. So when the volume is attached to worker node and it is ensured that it is surfaced on the file system of the worker node, then it is time to make it available to the pod. And as I explained earlier, it is done in 2 phases. The first step is to attach or mount this volume to a global directory on the worker node across all pods, and that is what happens in this method called node stage volume. So you are given the volume ID, the corresponding volume ID. You are also given the target path. This is the target path that needs to be that is for the pod actually. And then you gather all the details and then perform these steps. You create a directory for the staging target path. The variable is already defined here, and then you perform mount volume device path and staging target path. This volume device path is the path that got found in the previous step in the controller section. So this is the directory where the volume surfaces in the file system of the worker node when the volume attachment to the worker node is completed. So in this method, you have to go and get this volume device path by using a method. You need to figure out where, according to your environment, where is this volume device path is, and then you mount it to the staging target path. So when this method is executed successfully, the volume path is mounted to the global directory on the worker node. This is across all pods. There is no pod attachment yet. And unstaged volume will do the opposite. So it will be unmounted from the global target path. And I have a detailed logic here if you want to follow this, which supports multipath and all that. But ultimately, the unmount command is executed on the staging target path. And in the case of multipath, all the slave devices are also removed if needed. So once the volume is mounted to the global target path on the worker node across all pods, now is the time to examine how the same is mounted to a pod directory. So every pod running in Kubernetes or OpenShift environment has a corresponding directory if for each volume referenced in it, and that is done here, the node publish volume method. and you are once again presented with the staging target path and then the target path as well for the pod, and finally you perform the mount, the bind mount. Actually, there's a difference between the previous one. So bind mount between the staging target path and the target path. So this is binding the global target path on the worker node to the pod specific target path. So when this is completed, the pod should immediately come to running state, and if you log in inside the pod, you should see the mounted directory attached. So we're going to see all that in a moment. So this is the implementation of the node server. So let us quickly take a look at the third one, which is very simple, the identity server, which I think will be the same for any implementation of CSI. There's nothing fancy here at all. The probe method is invoked periodically by the CSI infrastructure in the Kubernetes or OpenShift environment, and this should return a value back. If this executable, the CSI plugin executable, crashed, then obviously this method invocation will fail. That means the driver is marked as unhealthy. So that pretty much completes the code examination. So now let us take a look at the Docker file that will be used to build a Docker image by the make file, by the make step, to create a Docker image before it is pushed to the image repository. And I'm using Red Hat 8 image, UBI 8 image, and here are some details about the driver. And then I'm creating this directory under the covers because this is defined somewhere in the source code. This directory should exist. And then I'm also creating HC config, which you don't have to do all this, but if your application, if your environment requires all this to be available in the CSI plugin, then you do whatever that is needed. And I copy the my CSI driver. This is executable that I'm building with the Go language, and it is getting copied to the root of the image, and it is made as an executable. And then I make sure the environment is up to date. And I also install sudo because in my case I was invoking sudo commands to do the mounting. And finally the entry point for this image is my CSI driver. So by the time this image runs, the my CSI driver will end up running on the corresponding worker node. So let me finish this with the make file again. So here's the build.make. Just to recap, this step will build everything we saw so far in the Go languages, and this step will perform the Docker login, and then this step will perform the building of the image, and this step will perform the saving of the image to a tar file, and finally this step will perform the push image. But who will do all this? So you can invoke this make file manually. You can do make Docker login, make build image, make save image, and then make push image, or you can do make push image that will perform everything except the Docker login. So instead of you doing it manually, I recommend you do it through some CI infrastructure, continuous integration infrastructure, and that is, in my case, I did it with Travis CI. So this Travis CI file, the YAML file, will help me to not only build the CSI plugin, but also create an image and then push it to the repository. And if you are familiar with the Travis CI, then you will understand what this is. This is where the glide is executed to prepare the imports and the prerequisites for the Go language code. And here is the make Docker login, and I'm conditionally invoking this only if the branch is set to official branch or whatever. Otherwise I don't want to make a login. And then make push image. So this will do everything. This will build the executable and then create an image and then save the image and then also push the image to the Docker hub in my case. So if you're familiar with Travis CI, then this is how you automate building and creating the image and then pushing it to the image registry. If you are using some other CI product like Jenkins or Concourse, then you will do something similar. So now it's time for to see the actual execution. So what I'm going to do is I have an OpenShift environment and I have 3 masters and 3 worker nodes. On that environment, I'm going to install this CSI driver, and then I'm going to ensure the CSI driver is healthy, and then I will create a persistent volume claim, and then I will create a pod, and I will explain the whole thing. So let's switch over to that. So the first step is to make sure you create a separate namespace, and I did that with the name CSI test. And then I make sure the nodes are all healthy with the OC get nodes command. And then I will execute some policy change. These are needed for the implementation. So this will ensure the cluster admin has sufficient permissions. And similarly, one more for the default user of the namespace. And the namespace in my case is CSI test. Okay, after this, my next step will be to set up what is called security context. So this is the file that I created. So here it is. So this file contains the security context constraints, and this is needed for my CSI driver to work. In your case, it could be something else, or it could be the same thing, whatever. I make sure the host path and the networking are all enabled in this case. So the host path is allowed, and then the host network is also accessible. So allow host network, and then allow host volume, direct volume plugin, they're all set to true. And I'm also defining these users, the 4 users in the CSI test namespace. So I do AOC apply -f sec.yaml file. Oh, sorry, -f. So it gets created. I can say OC get sec, make sure it should return with my CSI access as the name. So now it's time for me to process the template. The template is defined in this YAML file. So this is such a long file, so let us go through this very quickly. Here is the template name, my CSI, and then I have a configuration map. So in your case, if you are dependent on environment variable, you can define this, otherwise it is not needed. But I just wanted to show you how to create a config map inside the template. So in this, I'm creating an environment called env1 and set its value to 1. Maybe this environment is used somewhere in your stateful set or daemon set. So in that case, that will be a good idea to do this. So another good example of this is for creating a volume and deleting a volume, for attaching and detaching the volume to worker node. You may be invoking a legacy API or legacy application, and that application may require some credentials. So those things can be stored here in the form of a secret environment variable, secret config map. And this is the storage class that we will be creating. So you don't have to create the storage class yourself. Customers can create them, but it is a good idea to create a default storage class and then provide it here. So in my case, I'm adding a file system type as a parameter. so that when customers want, they can create another storage type for entirely different file system type. And this file system type is read by the code while creating a file system on the stage volume or publish volume methods that we saw earlier. And here is a service account. So from now on, there will be a bunch of objects related to each other for each of the stateful sets. So this is the attaches stateful set, a service account, and another service account for resizer, a cluster role, and a cluster role binding for attacher, and this is the second cluster role binding for resizer and also for attacher, and then the service for the stateful set. A port number is also defined here in case if you want to use it for debugging purposes. And here is the stateful set. And inside the stateful set, the most important thing is the container images. So here's the first image called CSI Attacher, and on Intel platform you can get it from Quay.io K8 CSI Attacher. Version 3.0.0 RC1 is the latest, and it takes these parameters. This is the community driven sidecar that is used for CSI purposes, and then it also requires an environment variable called address, and it should point to the socket, the Unix socket. And second image is the liveness probe for health purposes, and this here is the image for that, and it requires two parameters, the connection timeout and also the CSI address, the same CSI socket, Unix socket. And finally the image that we built, so it is treated as an environment, it's a parameter in this template file, which is defined at the bottom of this file, which we will see in a moment. And it takes these two parameters, CSI address, which is the same Unix socket, csi.sock, and it has got the section for liveness probe as well for health monitoring purposes. So that is about the stateful set for attacher, and here is the same for resizer. Pretty much the same thing except for the sidecar. The CSI resizer is the sidecar here, and version 0.5.0 in Quay.io K8 SCSI is the latest, and it takes CSI address as a parameter. And the other two containers in this stateful set are identical to what we saw earlier, the liveness probe and also the CSI plugin that we built. And now over to the service account for provisioner. So what we saw so far is attacher and resizer, and this is for provisioner, the third and final stateful set. So everything should be identical here. I'm just scrolling through this for your reference, and here's the stateful set, and this has got identical containers in it. The three of them. The one of them is, the first is the CSI provisioner, and here is the sidecar image, Quay.io K8 SCSI CSI provisioner version 2.0.0 RC2, the latest at the time of developing this video. CSI address and version, the debug, the --v equal to 5 means debug enabled, verbose. And here is a liveness probe, the same thing we saw earlier, and also the CSI plugin that we developed and its image. So let's go to the, so now we need to define the daemon set, and here's the service account for that, cluster role for that, and cluster role binding for that, and here's a daemon set. This daemon set has got two images in it, as we discussed earlier. One is the node driver registrar, and this is another sidecar, and this sidecar is Quay.io K8 SCSI CSI node driver registrar version 1.3.0, and this is what is responsible for registering this driver to the CSI, and it takes these parameters: CSI address and kubelet registration path, and this contains the same image again. The second image is the liveness probe that we saw earlier for health monitoring purposes, and then here is the CSI plugin that we developed as a third image in the daemon set. So daemon set is something in Kubernetes environment which will run only on the worker node, and when a new worker node is added, Kubernetes or OpenShift will take care of deploying a daemon set automatically on it, so which is really cool. And there are several volume mounts which may not be applicable in your case. I needed all this to perform mounting and detecting volume on the file system on the worker node and all that. So in your case, you may not need all these things. And finally, there are a lot of volume definitions. And finally, the CSI driver. So we need to define that also here and attach it to the CSI driver. And I needed, so these are the parameters. You can skip all these except the image repo, and here is the image repo that we built in the makefile svenkat.doc my CSI driver. I could have hard-coded this in the daemon set on wherever that's needed up there, but I decided to parameterize it so that if I change this image sometime later, I can do it in one place. And similarly for image tag. And that is pretty much the entire template. So I will be processing this template file and then create a output file, and then I will use the OC create -f to import that file. So let us see how that is done. So the first thing you need to do is run this command: OC apply -f my CSI v 1.0.0 YAML, the same YAML file that we were looking for a moment now. So this will make sure the template is imported into the environment. The next step is to do the process. So my OC process my CSI. My -CSI is the name of the template, and then spool it to a file called a.yaml file. So at the end of whatever we've done so far, we should be able to see the template and also the a.yaml file, which we will import now as OC apply -f a.yaml file. So this will make sure all the artifacts that we saw in the template be created. So everything got created. So now before we do anything else, we need to set some policy as well. So that is this one. Because the pod is going to be run in the privilege mode, all the service accounts need privilege mode as well in the policy. Similarly for provisioner and also for the resizer and also for the node. So all four, three of them belong to the stateful set and one of them belong to the daemon set. So when the whole thing is completed, let us do a OC get pods. So all these pods and all these pods are up and running, except one of them is in evicted mode. That must be due to the corresponding worker node not in healthy state. So that is okay. So only we have 3 worker nodes and one of them is in bad state. That's fine. We still have the other 2 worker nodes. And we also have to make sure the CSI nodes are also created. So OC get CSI node. So this also needs to be created. Otherwise, you should not proceed. So it took a while, maybe a minute or so, for the CSI nodes to show up. You can see, you may see the CSI nodes for all the worker nodes. You should see them, but in this environment looks like some of the worker nodes are not in healthy state. or at least one of them showed up, which is good, and the worker node 2 may show up any moment now. So now is the next step to go and create a persistent volume claim, so which I have defined in this YAML file. So here it is. The access mode is set to read write many. The storage class name is my CSI volume default. So this is exactly the same storage class we saw in the template a few minutes ago. And then I want to create a 1 gig volume claim. So now let us see if there are any volume claim already in place. There are no volume claims, and let us see if there are any volume, persistent volume. There are none. So now I'm going to OC apply -f dynamic pvc.yaml file. So it got created and it got bounded as well. That means it went through all the methods that we saw in the controller object, the create and publish volume methods. So they all went through successfully. So we have a persistent volume claim as well as corresponding persistent volume. Now it's time to attach this volume claim to a pod, and I have a file for that. So here it is. I'm creating a nginx image-based pod, and one of the volume is coming from the claim that we just created, example PVC Sridhar volume claim, and this my PVC is mounted under user share nginx html my CSI. So in my driver code, I did not implement it completely. I left it as blank. So after this pod is created, you will never see this particular directory. But if you follow the instruction that I gave, and if you do the same thing in your case, you should be able to. But at least the pod creation should go through. So let us see OC apply -f dynamic pod.yaml file, and it went through. And let me see if OC get pods. The container creation is going on. Let's see, watch OC get pods. Let's wait for the example pod to complete. So the pod got deployed, and let us do a describe. And you can see the volume example PVC Sridhar got attached to the pod, and it is supposed to be mounted under this directory user share nginx html my CSI. But since I did not implement the actual mounting code, even though it says it is mounted, it is not actually. So in your case, you need to make sure the pod directory is mounted on the pod by following the instructions from my source code. So this is how you develop a CSI driver and build it, push it to your image registry, and then consume it in stateful sets and daemon sets and all that. And I hope you enjoyed this video, and I will be producing a lot more videos on OpenShift in your future. Have a wonderful day, and I will see you all in another video. Bye for now.